How are you all doing this morning?
Doing well. How about yourself?
Doing pretty good. All right, let's get started. So I have a little bit of a problem here today because it looks like I did not save my work for my differential amplifier layout. So I lost my the NMOS bit for my differential pair amplifier. So I'm gonna have to redo that kind of quick. So while I'm working on that, what I would like you guys to be working on is making a schematic for the differential amplifier layout. That should be pretty straightforward. think I have my end well, there's gonna be my my end moth bit done correctly. I've got my sources tied to my body, which is going to get tied to my current source later. I've got a means by which to send signals over the guard ring for the drains of both transistors as well as our input voltage V1 and V2. So that all seems okay. So now I gotta do my NMOS or PMOSs. All right, so I think I'm pretty much back to where I was if we want to resume working on the layout here. I do need to wire up everything. So let's see. Stop giving me that. close together. Now I need to, let's see, look at my schematic diagram. Hmm. You know what? I'm going to do it with metal. That's going to have those guys. Yeah. What just happened? Why can't All right. These gates need to be tied together, but not with polysilicon. Actually, let me see how close I can get these guys to each other before it starts giving me errors. Still no errors. Let's see. This, I think I can fix. If I don't have the extension. All right, no errors. Okay. Let's put some labeling down. This is going to be the drain of M3. This is the source of transistor 4. Oh, sorry, this is the source of 3. Got all my gates lined up and all that jazz. This is the drain of 4. Here's the source of 4. All right, now I need to put a metal 2. Oh. All right, do this the other way. Okay, let me think. All right, so I need to put my guard ring around, so that's going to be in well. It needs to be, let's say, 75. 75 isn't quite long enough. Probably still not quite long enough. Looks like it might work. Less than 12 wide. So it's telling me that my end well is less than 12 wide. I think what it's referring to is the fact that right here, the end well is less than 12, but I think that will fix itself when I finish the ring. So let's see what happens. No, we need end well. Let's make this 5. 35. All right, so I'm going to have overlap there. It is going to hate that. And I need to put in well. quite long enough. All right. 9 errors. What are the errors? All right, so those guys overlap, which means this guy needs to be 5 wider. All right, no errors. Okay, so my source should be connected to VDD for each of these transistors. The drain of transistor M3 give me any errors. Okay. So the drain of transistor M3 is tied to the gates of M3 and M4. And that should also be tied to the drain of transistor M1. Let me see if I can, no, it's too much selected. No errors. No. Still no errors. Okay. So you guys with me? Haven't heard anything from you in a bit.
Yeah, we're here.
Okay. All right. So I'm just trying to double check here, make sure I've got everything legit. So this big guard ring up top is the body connection for the PMOS transistors, and it's going to be tied to VDD. This ring right here is the body connection for the NMOS transistors. It's tied to the source, and it's just going to be right now a kind of floating potential. So I'm just making sure that the source and the body are at the same potential so that I don't have body effects. This guy right here is going to be where my VN1 is from. This guy right here is where VN2 is from. So let's see, I need to wire the drain of transistor M4 to the drain of transistor M2. How am I going to do that? I'm going to have to use a metal 2 connection. Let's see. This guy's getting in my way. Messing up my symmetry, so I'll probably go back through and fix it later, but for now, let's see if that gives me any errors. It does not. Yeah. So wire that guy to, oh, guy's still getting in the way. Nope, I want it via metal 2. Oh, you pesky thing. All right, it's frustrating me, so I'll do it this way. Okay. All right. 18 errors, good gracious, what's going on now? Oh, it's because this guy isn't in there and it needs to be, I think. All right, no errors. All right, so my output voltage. Where do I want to take that from? Metal 2. All right, so this guy is where I'm going to take my output voltage at. So if I can ever find the pin, there we go. So I never remembered to do the metal 2 guy down here, so I'll do that real quick. So I'm going to export. This is VN2. This guy should be VN1. I think I named it, not exported it. All right. I'm just going to put a little piece of wire there, and I'm going to call this guy for now BDD. And I'm going to put a little piece of wire here for now, and I'm going to export this as IREF. All right, so I think we have everything wired correctly. Drain of 3 is tied to the drain of 1. Drain of 4 is tied to the drain of 2. Source of 3 and 4 is tied to VDD. Source of 1 and 2 is tied to where my current is going to come in. I can put in my input voltage. I can put in my other input voltage. I can measure my output voltage. So I think I'm ready for SPICE commands. Excuse me. So the first thing I'm going to do is I'm going to test this guy with ideal sources and make sure it's behaving how it's supposed to behave. So this is going to be multi-line text where I'm going to define VDD between that node and ground to be a DC voltage having 5 volts. Let's see. VN1 will be between node VN1 and ground, DC value of 0, sinusoid of 0, offset 1 millivolt, 1 kilohertz, VN2, 0, DC 0. So I'm just effectively, the DC signal on both of my input pins is going to be 0, and then I'm applying a very small sinusoid to pin to the input 1, and I'm hopefully going to be amplifying that signal. So I've got all those guys defined. Let's see, my current. IREF 0 DC 20 microamps, because that's the reference current that's going to be generated by our current mirror. I want to do a transient analysis for 5 microseconds, because that should give me 5 cycles, or excuse me, 5 milliseconds, and dot include models.txt. Alrighty. So just to make sure no errors there, let me run the well check because it's been a hot minute. No errors there. All right, let's cross our fingers and see if this thing works. So first thing I want to do is make sure that I didn't screw up something. So I'm looking at my reference current, and I'm going to change. I'm literally just making sure I put in the SPICE code for my reference current source correctly, because we haven't done anything like that before. We haven't used the current source before. So let's put this in 10 microamp. Yeah. And 50. All right, so it's giving me flat 20 microamps. So that's doing what it's supposed to do. So that's good. Now let's look at our input signal, 1 millivolt input signal there. So that seems right. I'm just making sure because we haven't used a sine function to this point. So I'm just making sure everything's groovy. All right, so now, oh, I guess I could have left that. So that's my input voltage, the moment of truth. All right, so my output voltage is doing something, so that's good. Actually, let me delete my input voltage. Okay, so it is sinusoidally varying. That's great. It's got a considerable DC offset that we're going to need to get rid of to make a comparison. So let's see. Looks like this guy is oscillating about 4.163 volts, something close to that. All right. And let's add our input trace back in. Okay, so we're putting a small sinusoidal signal in. We're getting a significantly larger sinusoidal signal out. We have a voltage gain of about what looks to be 27. We can check that really easily. I just put this guy on a peak. Yep, 26.7. All right. So in the ideal case, this guy is working as intended. So that's good news. All right, so then what do you guys want to do next? Do you want to finish building the schematic and we can test the schematic versus the layout and all that kind of stuff and make sure it's working properly? Or do we want to hook up our current mirror as the reference current and see that our 2 parts are working properly?
I'd rather build the schematic, I think.
Okay. All right, I'm gonna close out LT Spice for now, and then we're gonna jump into Explorer. I'm gonna right-click this library and create a new cell, and it needs to have the same thing as the old one, so differential underscore amplifier and make sure to click schematic. All right. So go over to components. I'm using the 4 terminal transistors. I'm gonna zoom way in. So this guy right here is going to be my transistor M1. It is a 10 by 2. I'm going to move this text. And I guess I'll leave it that size for now. So another transistor, I'm going to put it over here. This one needs to be mirrored, so I go to Edit, Mirror, Left, Right. This is M2. It has a width of 10 and a length of 2. Move that text out of the way. So my sources are tied together. Now I'm simply tying my body to that source connection. I have that little bit. Ooh, that guy didn't quite make it. There we go. Ooh, but it's not showing that it is connected. All right. This node is where IREF is, which if I could spell, that would help. And I'm just going to drop it down there. Now I'm going to build my PMOS transistors and get all that wired together and then worry about how I wire my PMOS to my NMOS. So let's see, select PMOS. I guess I'll do, oops, that's not what I wanted to do. This side first. So this is going to be M4A. It's a 10 by 2. And I'm just going to make a couple of copies of it. And then rename them M4B and C. Oops. These 3 guys are in parallel, so connect the gate to the gate to the gate. Connect the drain. Drain. Stop that. To the drain. Source to the source to the source. Body to the source. Body to the source. Body to the source. And move it up a smidge. All right. Here, here. So I'm going to export this pin as VN2. I'm going to export this pin as Vout. While I'm at it, I guess I can come over here and export. No. Control E, this guy is VN1. Okay, let's see. Now let's do transistor M3. And he needs to be mirrored. And then scoot it over here. This is a M3A. It's 10 by 2. Grab the text. There we go. B, C. These guys are in parallel, so wire the gates together. Wire drains together. And our sources up here. Tie our body to our source. So for our PMOS transistors, the gates are tied together, so I just took care of that. Then the gate is also tied to the drains of M3 and M1. So that's got that taken care of. So I think the only thing we have left to do is tie these guys to power. Let's see. So I'm going to export this as Control E, VDD, lowercase VDD. All right, so anybody see any? Oh, there's one huge mistake I've made here. I never set the splice model for a single one of my transistors. So this guy's got to be PMOS. PMOS. Wish there were a keyboard shortcut for this. All right, so there is our PMOS transistors taken care of. Still got to do the NMOSs over here. That's not what I want to do. All right. Okay, so now are there any other mistakes anybody catch me making, just to be sure here? So I have 3 PMOS transistors in parallel forming transistor M3A. The body of all of those transistors is tied to the source, which is tied to VDD. The drains of transistor M3 is tied to the drain of transistor M1 and also to the gate of transistors M3 and M4. For transistor M4, it's also 3 PMOSs in parallel. So that looks good. Got my sources for my NMOSs. I think everything's correct. So I'm going to go over to the layout and just steal this spice text. And let's check. DRC looks good. Simulate. Add traces. Okay, so we want to see V out. $3.915. So let's subtract from this minus 3.918. It's making it go around 0. And let's look at our input. Add traces. And 1. All right, so we look like we have a gain of approximately 25. So just for the sake of argument, I'm going to make this smaller. Wait, actually, I need to make this smaller. And this smaller. And I'm going to pop over to my layout view and run the simulation as well. So let's see, V out. So our voltage is appreciably different here. Minus 4.163. Trace and 1. Let's try to take a peek at these guys side by side. So the one on the left is for the schematic, the one on the right is for the layout. So we can see, let's see, what's the difference in those DC offsets of our output? So 4.163 for our schematic minus 3.918. So we are off 245 millivolts, so approximately 1 VDS sat with respect to our voltage gain. Our layout has a slightly better voltage gain of 27 compared to the 25 we see with our schematic. So they're behaving similarly, but it's not quite spot on. One possible reason for this is if we look down here in our schematic code, we're given a warning that there's no ground connection. So we don't have an explicit ground specified in our schematic view. But we do have an explicit ground specified, I think. Let's see. All right. Nope, also no ground connection for the wells. So for the body. All right, so that's not it. Well,
So if we see differences, is this like the general method that you would suggest for trying to figure out why they're happening, is to like scroll through the warnings and the whatever you get with LT Spice when you simulate?
yeah, I mean, so this, the difference here, so I mean, the factor 2 in the voltage gain isn't all that much. I'm wondering about where this 250 volt or 250 millivolt change in the DC offset is coming from, or whether it matters. And so what I mean by that is it works. It's doing what it's supposed to do. Like one thing that the schematic view isn't going to take into account is the ton of parasitics that we have in our layout view.
Yeah, for sure.
So I'm just trying to kind of look at things and make sure things are doing reasonably what I expected, and if so, I'm happy. So I'm going to close both of these guys out. And I'm going to run a layout versus schematic, which that is this guy. And again, the only thing that it's telling me that it sees different is that VDD is a power connection in one and just a voltage in the other. So it sees them as the same thing. So that amount of variation, I'm probably going to let that slide and see, like, it's working how it's supposed to, so I'm pretty pleased. All right, so let's pop back over to that schematic view because this will be a little bit easier to do here. So now what I'm going to do, I'm going to leave this exactly how it is, except that I am going to press Control I here. So I'm going to put an asterisk in front of that iref command because that's effectively Spice's way of commenting something out, because I'm about to hook up our current mirror and we're going to see how this guy performs with that. So I'm going to take our Cascode current mirror schematic, just drop that bad boy in. Thank you again, Aiden, for remembering how to make this work. So I'm going to expand this guy and hit OK. So this guy has a bunch of Spice text associated with it as well. I have already gone through apparently and commented out what we don't need here. So we don't need multiple VDD declarations, so I commented that one out. We are still explicitly biasing the gate of our PMOS current source, which is kind of driving this, or that's how we've loaded this current mirror with 3.88 volts. And I think that's the next thing that we're gonna go over. I'm no longer letting that drain source voltage VDS4 range from 0 to 5 volts because that's effectively the output of this current mirror. And I don't need to declare my include CMOS models statement again. So I'm just going to slide this guy down here, and I'm going to take this wire and connect it to that wire, and that may be all we need. So let's run a simulation here. First, let's check DRC. One error. There's an unnecessary pin. That's fine. I'm not going to bother fixing that. All right, let's make this guy bigger. Here's a problem. Saving all this silly business from earlier. All right, so here's V out. And it looks funky. So that's some transient happening at the beginning. So instead, let's close this out. And I'm going to change this guy from 5 milliseconds to 10 milliseconds. Just so hopefully we can see it in a more settled state. So we've got some business going on here. So let's see, here is approximately thing. So let's subtract minus 4.57312. And I want to start looking at this guy at, let's say, about 4.5 milliseconds. So that I don't have that weird transient thing going on. Okay. So let me plot my input signal as well. All right, so we have a bit of a problem here. Our input signal, 1 millivolt sinusoid, is significantly larger than our output signal, which is I think it was around 80 microvolt. Let me see. So it's still got a little bit of a DC offset there. But yeah, so it's ranging from, let's see. So this is about 70 to about minus 90. Yeah. So it's about an 80 microvolt signal. So what is happening? Anybody have any ideas? Why did our gain of 27 go down very, very significantly, right? So we have 0.08 divided by, well, we had a gain of 27, and now we have a gain of 0.08.
I mean, could it be some issue with the biasing voltages with the current mirror? I don't really know, to be honest.
All right, so I'm gonna close this out and we're gonna look at the schematic. So what's happening here is that before we had an ideal current source, right? Here, effectively placed between this node and ground. And so the source voltage here was allowed to go negative if it needed to. And in this case, it would have needed to because we had a zero input DC signal on VN1 and VN2. So for those transistors to be in saturation, that would mean that the voltage at the source was negative. If we have, but now that's effectively saying that this drain source voltage here at transistor M4 of our current mirror is negative, which means this guy isn't operating in saturation, nor is this guy. So effectively what we've ran into is a problem called headroom, okay? So we are not going to properly amplify our signal until our input voltages are above the VDS that's necessary to turn these guys on. If we looked at, let's see, just our current mirror schematic and run a simulation here. Tool, simulation, right by step. Can't find. All right, hold on. Oh, it's because I have all these asterisks in, so it's not finding the models that we need. All right, tools, right by stick, add trace. So we want, let's see, ID for M1. And ID for M2. Where this guy looks like it needs to be negative. All right, let's add VDS4 as well. This isn't the plot that I'm expecting. Oh, well. So I'll just tell you what the answer is then. So really what we were expecting is that for these two transistors to be in saturation, our voltage needs to be about 1 volt there, because it's going to be, I think it's like 1 volt or 1.25 volts approximately. I don't remember if it's 2 VDS sat above VTH or just 1, off the top of my head. So what we're going to do, I need to fix all that, because if I don't change all those comment those things back out, then this guy is going to freak out. So what I'm going to do is I'm going to change the bias voltage that's supplied. So let's just bump this guy up to 2 volts. That's well above what it needs to be. Oh wait, actually that's wrong. This guy needs to be 2 volts. And let's put 2 volts here. So in this sign declaration, the first thing is the DC offset, then it's the magnitude of the AC signal, then it's the frequency, and then we could also put in the phase and other things like that, but I'm not worried about it. So I'm going to apply this, and I'm going to run this. And let's look at our output voltage. So it looks wild, okay? Looks a bit crazy. I am going to subtract out the DC offset here, which is 3.9 let's see, 2.1 volts or so. And you may be saying to yourself, well, gosh, this looks like the hottest of garbage. Why do we care? If we look at VN1 minus VN2, we can see that it is actually amplifying the input signal. I don't know why LT Spice is doing this for me. I can't figure it out, but when I was playing around with this yesterday, if we look at the input signal by itself, so it's like sinusoidal for half a cycle, then triangular for half a cycle, then sinusoidal, back and forth, back and forth. I haven't quite figured out why it's doing that. I'm gonna work on that this weekend. But we can see pretty definitively that our amplifier circuit is doing what it's amplifying that input signal. So let me again minus 3.9, that's not a 3.921 V. So it is indeed amplifying the crazy looking input signal with a gain of around between 25 and 27, something. So I don't know why the input signal is behaving poorly. I wasn't able to figure that out yesterday while I was playing around with things. But the current mirror that we're using to bias this thing is doing effectively what it's supposed to do, because we're getting amplification with roughly the same gain. So let's jump here into our differential amplifier layout and see what happens when we drop in our NMOS current mirror bit and don't use the ideal amplifier. All right, so I'm going to need to slightly modify things here in my in my Cascode current mirror, because I need to get a connection from where I have this export of VDS4, which I'm going to move. Actually, let me delete this. All right. Okay. I'm just making sure that, okay. Come on. There we go. So I need to get that signal over the ground ring and connected elsewhere. So I'm going to do the exact same thing I did earlier. I'm going to put a 9x4 guy, wire that, run some metal 2. Run it to the outside. No, I don't want the pin. I want the, there we go. 9, either end. Now I'm going to export this pin back to VDS4, just so that I'll have it. And hopefully that exact same thing got, oh, well, it didn't save the fact that I put that guy in there, or maybe I deleted it. So let's see, 5, 2 errors. So I need to play around with this real quick. So I'm going to delete this guy, and I'm going to create a contact here, and let's make it 9 in the X direction. And if I can find a pin, there we go. IREF. Now we will go to this spice code. Comment this guy out. Fix our input voltages to where we're not. Here. And then while I'm at it, I think I need to change this spice code because I don't think I did it for this one. Oops, this one. So I don't need that extra VDD. I don't need this. I don't need this. I don't need that. All right, so cross your fingers and let's see what happens. Let's run the DRC again. 0 errors. Out. Not remotely what I'm expecting. VN1 minus VN2 also not remotely what I am expecting. So there's got to be an error in my code or something then. So from node VN1 to ground, there is a DC value of 0, and then sign. Let me run this again, look at some stuff. So that's supposed to be 2-volt DC offset with a 1 millivolt sinusoidal signal. That is not remotely what it's looking like. That traces BBN2 is just a 2-volt. So that is doing what it's supposed to. But why isn't my so just to be clear here, if I have that disconnected, put this in, and trace 2-volt like it's supposed to be. Banana's crazy input signal. Still, again, don't understand why, but it is what it is. Let's look at V out. So we do have, again, that weird amplification. So I think the issue is that it's freaking out because of how strange the input signal looks. So I think I'm gonna have to figure out how to fix that. Okay, so I'll do that later because we only have 10 minutes left of class. So things are actually looking pretty good. Technically speaking, if you wanted to get down to brass tacks, if we look at this schematic here, we have created a single stage op amp. So in some sense, we have actually accomplished our goals for this class. Now, a couple of things here. One, we're biasing our reference current mirror with not a random voltage per se by any stretch of the imagination, but it's unlikely that we are going to have access to a 3.88 volt source. So one of the things that we're going to have to do is come up with a biasing circuit to generate that voltage of 3.88 volts. There's two ways that we could go about doing this. One is very simple, and it would, I guess, technically work, but it's not really a good idea because it's very dependent on variations in temperature and power supply, and that would be to literally just put a resistive voltage divider there with the ratio of the resistors set to give us that 3.88 volts. And the other smarter method is to use what is called a beta multiplier reference circuit, which I'm showing here on the screen. So this is from the textbook. The explanation, if you have the newest version of the textbook, so version 4th edition, the derivation for all of this kind of stuff is on pages 631 through 634. If you have the 3rd edition digital copy of the textbook, which I think some of you told me you were able to find online for free, so you saved yourself a couple of $100. Let's see, this is on page 625. So supply independent biasing starts at page 624, probably lasts about 3 pages. So that's the explanation for the beta multiplier circuit. This is what we are going to be building next, I think. And this is probably the most complicated part of our op amp, at least to this point. If we cycle back around to our schematic diagram thing here. Again, another thing that we need to take into consideration is that while we do have an op-amp circuit, that beta multiplier reference circuit isn't going to increase the voltage gain of this guy by any stretch of the imagination. It's literally just going to supply that 3.88 volts here. It's actually not supplying, it's going to supply 3.88 volts, but what it's doing is it's creating a bias level that is exactly 1 VTH plus VDS sat below VDD for biasing PMOS transistors. So it wouldn't matter what your voltage VDD is, it's going to bring that bias voltage down to the exact level to set this guy in saturation, regardless of if we have variations in the power supply, which is why it's called supply independent biasing, and it's also why we're going to use it. To increase the voltage gain, we're going to have to add a second stage. And probably because we're getting so late or so close to the end of the quarter, we'll simply use a, let's see, a simple common source amplifier, you know, a simple gain increasing stage to hopefully jump our output our voltage gain from 27 to somewhere on the order of a few hundred to a thousand or so. So that's what we've got left in the class, taking our single stage amplifier, making a couple of modifications to be able to increase our voltage gain, and then we will be out of time. All right, so if you have the textbook, either a physical or digital copy, you can go ahead and start working on either your layout or schematic representation of your beta multiplier reference, and that's what we're going to be working on probably most of next week because it's a large circuit that we've got to implement. Any questions or anything?
Yeah, sorry, one more time. What were the pages in the textbook? I just missed them, sorry.
Yeah, do you have the physical copy of the 4th edition or do you have a 4th edition or the 3rd edition? Let's start there.
I have the 3rd edition.
All right, so the 3rd edition. So it looks like page 624 is where it starts.
All right, good deal, thanks.
Yeah, all the derivation, and then this picture itself is on page 625.
Sounds good, thank you. I'll take a look through that and read it.
Yeah, one thing I want to point out here, so there's a startup circuit here. It says it's important. The reason why it's very important is that this is a positive feedback circuit, and this startup circuit causes it to effectively snap to a stable biasing position. This, if you notice right here, this 10x1 transistor labeled MSU3, so the startup 3 transistor, we can't do a 10x1 transistor in our process. It literally would not be allowed. So what would we do to fix that?
A 20x2 maybe.
Exactly right. We literally just scale up both the width and the length. Another thing to point out here, this 6.5 kilo ohm resistor, this is a biasing resistor that effectively sets the stable operating point for this system. So it's not going to be a hard and fast rule that this is going to be 6.5 kilo ohms. For us, it might be a little bit more, it might be a little bit less. We're going to play around with that value. But as far as the size of all the transistors, all that's going to work for us, except we need to change this guy to a 20 by 2. I can't draw a 2 with my mouse to save my life, apparently. All right, any other questions?
Yes, just briefly. In my diff amp, when I was running my Spice model, it seems like I'm getting like a gain, at least on the output, it's like a 4 point some change volts on the output, which I don't know if that's what that even means, if it's wrong or right, but.
So you're getting 4 volts and it's oscillating on the output?
Yep, it looks like a clean oscillating sine wave.
Huh, I wonder why you're, share your screen. Or actually, hold on, let me stop sharing so that it will let you share your screen. Advanced sharing options, everybody can share. Okay.
Let's see, share, Bob. You need to look at, oh, shit.
You gotta
There.
share your LT spice, right?
Yeah, I was gonna say, I think, there you are. My power went kind of weird for like a second. Yeah, hang on, let me just do that real fast. Spice stack. Add trace. V out, go. Need me to add any other traces?
No, so I'm just gonna look at this real quick. 4.190 minus 4.135. So 55 divided by 2. So you're getting a gain of 27.5 millivolts, or 27.5 volts per volts, which is really spot on to what we're doing. I'm very confused as to why your output looks nice and pretty and mine looks like the hot piece of garbage. Go back to electric real quick. And so you got your spice codes all stacked up on top of each other. So okay. So scroll to the left so I can look at that other spice code real quick. All right, so I think one reason why it's looking good is because you're still forcing 20 microamps of reference current to flow through, even though you're connected to the other.
Oh, okay, okay.
Comment out the IREF line. So you've still got effectively you have a 20 microamp current source in parallel with that current mirror.
Gotcha, so it's completely just, that current mirror is not really doing anything.
Yeah, I think that's what the case is. So comment out that IREF bit, and let's just see what happens.
And then there it went weird again.
Yeah, it's still, so it's a little bit sinusoidal and all that kind of stuff. So you might need to look at it for more than 5 seconds. Also, I bet your voltage gain is going to be teeny tiny. And I say that because your DC offset levels are so low that it's going to force those transistors to be in deep in the triode region. So yeah, okay. So just a couple of little things there, but you know, we'll figure it out.
Alrighty.
All right. Well, thank you for sharing your screen and all that kind of stuff. We can look at things.
Dr.
All right.
Hartman,
Yes.
I have a question about my schedule if you want to stay on.
Sure.
After this.
So everybody else can bail so I can advise Grant.
All right, have a good one.
All right. Thank you, guys.
All right.
One more thing, I'm sorry. Is tomorrow's advisory meeting, what time is it?
Oh, I'm sorry. I forgot to include the time. So it starts at 2.
Got it. Thank you.
Yep. So just the same as class time, but it will not last 3 hours. I will be super furious if it lasts 3 hours.
Thank you.
Yep.
Have a nice day.
You too.
Okay, so I looked for that math class with Dr. Dye that he had talked about.
Yeah, I think I misspoke. I looked at my transcript and it was Math 574. So the PDE classes are the ones where you learn about the modeling and all that kind of stuff.
Gotcha. Okay, yeah, he's teaching numerical PDE solutions next quarter, but I don't think I can take that because I didn't take PDE. So
Right.
We had said that there's really no math classes I could take next quarter. However, Ms. Kimlin sent out the email list with all of the classes that have been offered, and it doesn't look like there's any graduate level math classes offered in the spring.
I'll have to check with Galen. because I'm, like, if you look at getting a, like, if you look at, I want to see, hold on, let's see, LaTeX Math Master. I don't know why my internet's being so slow in my office. Oh, tells me that's down. All right.
Did you see the email I sent you a few days ago?
Yeah, I glanced at it and then I got busy and forgot.
Oh, you're good. I included the class list that I was talking about.
Right.
Um,
So to get a master in mathematics here at Tech, let's see, of the only required classes for you to take, and I know you're not getting a master's in mathematics, so I'll explain my logic here in a second, but the only 500 level math class that you're required to take is Math 574. All of the other ones, it tells you to choose from a bunch of different 400 level math classes. So those 400 level math classes must be considered graduate credit as well.
Okay.
So I just need to talk to Galen about how we make sure that that Math 400 something counts as a graduate class for you.
Sure. Okay.
That should significantly open up the number of math classes that are offered, because the 400 level, like here it says Math 407, 414, 415, 435, 460, and 482 are would all be considered for graduate credit.
Yeah, that would be perfect. 'Cause I think 482 was something I actually wanted to take.
Okay, so I will talk with Galen in the next day or two about how we make sure that that counts.
Perfect. So I should just hold off on my plan of study until then, or do you want me to just put a class and turn it in?
Put a class and turn it in, because they're going to make you redo it right before you graduate anyway.
So I'll do that.
All
All right,
right.
I think that was it. Thank you.
All right, cool deal. Catch you later.